Okay, so today we're gonna start a new topic that I have mentioned before in this class, and this is the introduction to integer programming. Hello, good. The introduction to integer programming, and as I mentioned at the beginning of the semester, at some point we were going to transition to how to solve problems in which you are required to have decision variables that are integer. So meaning that if you are looking for to make a decision that requires a number that is a complete integer value, such as the number of products that you need to produce, for those type of problems, you need to have a decision that is integer. So if you end up with a solution of 3.5, that's not telling you the information that you need. You need a solution that is in terms of 3 or 5, or 3 or 4. So that's the type of problem that we are going to address. So far, again, we were focusing on problems that have decision variables that were allowed to be fractional numbers. Now we're going to focus on problems that are forcing your decision variables to be integer. So this goes through these slides goes through the objectives of this semester, and as you have seen so far, I have been linking those objectives with we've been doing in class. So so as you can see, we have covered all those objectives so far. And now we're going to add this extra layer that is basically covering all these course objectives, in which we are going to be focusing on solving problems that are requiring decision variables to be integer. So the learning objectives for today first is to explain how to formulate integer programming models. There's not going to be a major difference between what you know already and what we're going to explain today. There's only one small detail that you need to be aware of. And then we're going to discuss how to solve integer programming models. So the agenda, we're going to go through the introduction, and I'm going to present an example just to illustrate the point. And then we're going to discuss the different type of integer programming models. We're going to go into some specific applications for formulating integer programming problems, specifically the capital budgeting allocation problem, the fixed charge problem, and the set covering problem. And finally, the last part of the lecture will look at solution methods, specifically the branch and bound method. Something that you need to understand is that the simplex method cannot be used to solve integer programming models. So we have to find another way. And there's an algorithm called the branch and bound method that is designed to solve integer programming models. However, the simplex will come into play as we solve these problems doing the branch and bound method. So let's look at the introduction. Integer programming is a mathematical optimization program in which some or all of the variables are restricted to be integers. So you will see when we get into the different type of integer programming models that they're the pure integer programming models. And there's also the mixed integer, which allow you to have some decision variables that can assume fractional numbers, and some of the decision variables that are going to be restricted to be integer. So to illustrate the importance of integer programming, we're going to look at this example, which is the TVA Airlines problem, which is an example where integrality matters. So this is a small regional company that specializes in short flights in small airplanes. The company has been doing well and has decided to expand its operations. And the basic issue facing management is whether to purchase more small airplanes, to add some new short flights, or to start moving into the national market by purchasing some large airplanes, or a combination of both. So the question is, how many airplanes of each type should be purchased to maximize their total net annual profit? So here's some information. we have the capital available is 100 million. And then we have some information about the net annual profit per airplane. For small airplanes is 1 million. For large airplane is 5 million. Purchase cost per airplane is 5 million. Purchase cost per airplane for large airplane is a lot more, 50 million. And for small airplanes, the maximum we can purchase is 2. So if we try to formulate this using linear programming, we're going to have 2 decision variables. One will tell us how many small airplanes we're going to purchase. L will tell us how many large airplanes to purchase. And the objective function will be to maximize our profit. So as we already saw in the table, we have 1 million for small airplanes and 5 million for large airplanes. And we have some capital constraint in terms of capital available. So we know we spend 5 million in small airplanes, 50 in large airplanes. So the summation of both has to be less than or equal to the amount of money that we have available. And we also have a constraint for the small airplanes. So we cannot purchase more than 2. And as we did in linear programming, most of the time we set up our decision variables, like in this case, to be greater or equal to 0, because we cannot purchase -1, -2, -3 airplanes. So our decision variables in this case will be positive. So if we solve this problem using the graphical method, we can set up our constraints. So this is the constraint in terms of how many small airplanes you can purchase. So less than 2. And then you have the second constraint, which is in terms of the capital available. And as we learned, we have the feasible region, and when we need to plot the isoprofit line, and we move in this direction. So the optimal solution for this problem using linear programming will give us a fractional value for the large airplanes. So as we explained already, from a practical perspective, this is not a good solution. We know that 1.8, we cannot purchase 1.8 airplanes. So that's the problem. So linear programming formulation, we have this divisibility assumption of linear programming. Decision variables in linear programming model are allowed to have any values, including fractional values, that satisfy the functional and non-negativity constraints. Variables are not restricted to be integer values. And in this problem, since the number of airplanes purchased by TVA must have an integer value, the divisibility assumption is violated. Okay, so now we need to fix this problem. So how do we make this model provide us with decisions that are practical in the sense of knowing, okay, this is exactly how many airplanes, or this is the strategy that I should follow. So if we go back to the formulation, you'll see that for the integer programming formulation, everything's going to look the same until we get to the last piece, in which we are also forcing our decision variables to be integer. Okay, so that's going to have an impact on the feasible region. You remember the feasible region for this problem is this area. So that's the feasible region for the linear programming model. But now we are adding this extra limitation or extra constraint, which we are forcing the decision variables to be integer. So when an integer programming problem has 2 decision variables, its optimal solution can be found by applying the graphical method, which you already know. So we are also going to graph the feasible region for the LP relaxation, meaning that we're going to graph the feasible region for the linear programming model. We're going to determine the slope of the objective function line, which is what we're going to use as the isoprofit line. We're going to move a straight edge with this slope through this feasible region in the direction of improving values of the objective function. But instead of stopping at the last point in the feasible region, we're going to stop at the last instant the straight line passes through an integer point that lies within the feasible region. This integer point is the optimal solution. So let me show you how that looks like. So now our feasible region is no longer that shaded area. Our feasible region is now demonstrated by, you'll see, so we plot the constraints. This is the LP relaxation feasible region. But now we are adding those dots, those black dots into the feasible region. Those are the points that are integer in terms of the solution. So we also plot the direction of improvement based on the objective function, that this is the isoprofit line. But instead of moving that line all the way to this point, which is the optimal solution for the linear programming model, now we're going to stop into the last point that has an integer value in the feasible region. And that last point that having an integer solution in the feasible region is this point. So the optimal solution for the integer programming model will be that point, which is telling us that we should buy only large airplanes. 0 small airplanes and 2 large airplanes, which makes sense, right? Because those were 50 million each, and we have 100 million in capital available. So 2 times 50 will be the 100. We'll be consuming the whole budget. So that will be the solution. And you can appreciate the difference, right? Now we are no longer going into the last point in the feasible region because we know that that point might not be integer. This is from the graphical solution perspective, which is, again, the idea is to illustrate the point. Then we're going to transition to larger problems. But we are going to be stopping in that last instance in terms of being an optimal solution that provides integer values. So why do we need integer programs? There's some advantages of restricting variables to take integer values. Obviously, our solutions are going to be more realistic. But I want to stress this point. Integer programming models are more difficult to solve than linear programming models. So the advantage is that they provide more realistic solutions, but the disadvantage is restricting variables to take on integer values is that they are difficult to model and very difficult to solve. So in this picture right here, I'm trying to illustrate the difference between the feasible region of the linear programming model and the feasible region of the integer programming model. And as you can see, that feasible region for the LP model is bigger. And the integer feasible region will be inside the feasible region for the LP formulation. So, yes, go ahead.
So, why don't we, if you work with like airplanes, for example, so we not need the individual, right?
Yes.
So, why don't we work with problem and then just round down?
Yeah, that's a good question. So the question is, why can't we just work with the solution of the LP and then round down, you said?
Yeah.
So for example, here, right? So this is the optimal solution for the linear programming model. So how do you make a decision here? Basically, you have 2 and 1.8. So how would you design a strategy in terms of rounding out, rounding out? Are you saying that 2 big and 1 small? Okay. So if we go back to our model here, two smalls, I say, right? 2 small and one big, right? So so the price of small airplanes is 5. So it will be 1 times 50, 2 times 5, right? So it'll be 60. So you still have 40. So you're not consuming the whole thing. And that's the issue. That could be a solution, but that would not be the optimal solution for you to take on this problem. That is a solution, taking 2 airplanes and 1 small, 1 big, 2 small, but that's not going to be the solution that's going to give you the maximum profit. And that's the challenge. And what you just mentioned, when you go to practice and to industry, since integer programming models are more difficult to solve. There'll be people in industry that will use that approach. They will solve the problem using linear programming, and will try to guess in which direction you go. Most of the time, that will give you a suboptimal solution, which is the case here. And you 2 and 1, yes, it's a solution, but you're not using the whole budget. So good question. So that's why we need these strategies to help us find the optimal solution for the integer case. So then moving forward, there are, and again, we are gonna, right now, I'm using these 2 decision variable problem just to illustrate the point. So you see what's going on, but then we're gonna transition to larger problems that we cannot solve using the graphical method. So before we get into that, as I mentioned, there are different types of integer programming models. There's the pure integer programming problems, are those where all the decision variables must be integers. And something that I always like to mention is what we are learning in class right now is the latest methods that have been developed, but there's continuous research on solving this type of problems. So every year there will be some new papers of people coming up with new methods on how to address this problem. So this is a field of research that is still open in terms of finding better ways. And why is this important? Again, as we move forward in this data era, we have access to all this information. Companies are becoming global in the sense of logistics, trying to make decisions that impact their business at the global level. It's very important for us to find new ways to solve these problems quickly. Like the methods that we have now, they're good. They will be able to solve problems, to large instance problems. And with the computer power that we have right now, they might take, for very, very big problems, they might take 1 day, 2 days to get a solution. So that's why there's continuing a lot of research being done in this area, trying to find better ways to minimize the solution time by finding different algorithms that can help us solve these problems. And you'll see why that's a challenge. There's a combinatorial aspect in these problems in which you are trying different combinations of solutions, and you're trying to find the right direction to get that to that optimal solution quicker. But we'll talk about that in a minute. So mixed integer programming is another type. So pure integer programming, all decision variables are integer. Mixed integer programming problems only require some of the variables to have integer values. So you can have a combination of integer and continuous decision variables or fractional decision variables. And then there's a binary integer programming problems, are those where all the decision variables are restricted to integer values and further restricted to be binary, 0 or 1. So most scheduling applications will have this type of decision variable. We saw some applications in our discussion of formulation. You were able to solve some of them for the scheduling of officers, scheduling of ambulances, and so on. You saw that the solutions were 0s or 1s. Sometimes linear programming models have a structure that will allow you to, based on the structure of the problem, you will end up having integer solution values without forcing the decision variables to be integer. But that's not the case for all of them. Okay, and those problems that you saw in the formulation lecture, they have that structure in place in which you can obtain decision variables that are binary without having to force the decision variables to be integer. But that's not the case for most integer programming models. So binary integer programming problems forces the binary or the decision variables to be binary in the sense of assuming values that are 0 or 1. So Here's a summary. So these are the three types of integer programming models: integer, mixed integer, and binary integer programming. And again, there's people specializing in research on pure integer program, people specializing on research in mixed integer programming, and people that specializes in research in binary integer programming. So there's communities in different universities that are working on these different areas in terms of research. So LP obtained by omitting all integer or 0, 1 constraints on stochastic or on variables is called LP relaxation of the integer programming. So the idea, for example, or what this is trying to say is when we have an integer programming model and we want to have at least to get an idea of how the solution will look like, we can relax the constraint that makes the decision variable integers and solve the problem as a linear programming model. That's what's called the LP relaxation of the integer program. So some practical applications in terms of formulation. The capital budgeting allocation problem. So you have a company that is considering 6 investments, and here's the information about the investment. The cash required in thousands for each investment, and then the net present value added also in thousands for each one of the investments. There's cash available for the investment is 14,000, and StockCo wants to maximize its net present value. So the question is, what will be the optimal strategy? As a note, an investment can be selected or not, so we cannot select a fraction of an investment. So if you want to go for investment 2, then you have to go for the whole thing. You cannot buy the fraction of that investment. So the question is, what's the optimal strategy? If you have this money available, what will be the best strategy for you? So if we formulate this as an integer programming model, these are decisions that are 1, if we invest in project I, or 0 else. And the objective function will basically maximize the investment net present value, which is what we're trying to do. We want to maximize this in net present value. And then we're going to have a constraint, a single constraint that is going to tell us, okay, you have these opportunities, you can only invest in some of them, and you have to make sure that you don't go over budget, which is 14,000. Okay, so this is an example of a binary decision variable problem in which you are letting your decision variables to be 0 or 1. You want to make sure that you select which investment you want to pursue, and you have this limitation in terms of capacity. Yes.
Can we go back to the problem?
So the cash required, these are the coefficients that are used in the constraint, and these are the coefficients that are used in the objective function. And then the constraint right-hand side is this amount, the amount of capacity in terms of budget that you have available. So this type of problem is called, or the example one, the capital budgeting allocation problem. Why is the problem with the characteristic of the previous problem called the Snapshot problem? So this is a very well-studied problem in linear programming and integer programming operation research in general, because it comes in different applications. And it's called the Snapshot problem because it is an fraction, considering the simple problem in which you have a hiker trying to fill her knapsack to maximum total value. Each item she considers taking with her has certain value and certain weight, and overall weight limitation gives us the same single constraint. So if you have a problem in which you have a capacity limitation and you're trying to decide how much you can put into this capacity without exceeding the actual capacity in terms of your decisions, that's typically called a Snapshot problem, which is what we saw in this problem. You have a single constraint, it's a capacity limitation constraint, and you're trying to decide which things to bring into the solution without exceeding this amount. Practical applications for this type of problems, as we saw, project selection and capital budgeting allocation problems, storing a warehouse to a maximum value given the indivisibility of goods and space limitation. So if you have in charge of a warehouse and you have this much space, trying to solve that problem and allocating space to products, you can solve that problem also looking at this formulation. Another example of an integer programming model is what is called a fixed charge problem. So here we have a company that manufactures 3 types of clothing: shirt, shorts, and pants. And we have the clothing type, the labor hours, and the cloth materials that are needed. We also have the sales price and the variable cost of producing these items. The machinery needed to manufacture each type of clothing must be rented, and the following rates apply. So for the shirt machinery, we have to pay $200 per week. Shorts machinery, $150 per week. And for the pants machinery, we have to pay $100 per week. Each week, 150 hours of labors and 160 square yards of clothes are available. So in this problem, we are not only trying to determine how many type of products we should produce, but also we have decisions in terms of whether or not we should rent a machine for those purposes. So if you're going to produce shirts, you have to rent a machine for the shirts. If you're going to produce shorts, you have to rent a short machine. And if you're not producing pants, then you don't have to rent that machine. So that's a problem that we are going to formulate. So what is the optimal strategy? How many of each type per week are we going to produce? So our decision variables, we have the number of shirts, number of shorts, and number of pants produced each week. And we also have another group of decision variables that are also integer, but in this case, those are binary. The ones at the top are not binary. Those are just integer, but the Y1, Y2, and Y3, those are binary. And Y1 is if you are manufacturing shirts, Y1 is going to be associated with the renting of that machine. If you don't manufacture shirts, then you don't need to have a machine, so that will be 0. So that's what this is trying to say. If we have an xj that is greater than 0, meaning that you are manufacturing that product, then we have to force that yj to be equal to 1. However, if xj is equal to 0, then we know that we don't need that machine, so we're going to force yj to be equal to 0. So our objective function is going to look like this. We have a profit that we are making by the money that we are making by selling the products, $12, $8, $15. And then we have the variable cost of producing those items, $6, $4, and $8. And then we also have a cost associated with renting the machines, $200, $150, and $100 for product type 3. So our objective function is going to be that equation right there, which has a combination of x and y. So if we solve this piece for the x1, x2, and x3, this is going to be smaller function, 6x1, 4x2 plus 7x3 minus the cost of renting the machines. So what are the constraints? We have a labor constraint. We have 150 hours available. So we have a limitation in that sense. And we are also having information about how long does it take to manufacture each product type. We also have a materials constraint, 160 square yards. And we know how much material is needed per product type. And then we know our decision variables have to be integer. Binary variables have to be integer as well. So if we only formulate the problem like this, I can tell you this formulation is incomplete, right? Because we have to have some way of connecting the decision variables y and x. To solve the problem just like this is going to be the optimal solution. So why is this wrong? Do you know? Can you tell me why this solution is incorrect?
I'm trying to understand the objective function.
Okay.
Maximize
So you're trying to understand the objective function?
Yeah.
So the objective function is based on the sale price and the variable cost.
yes. One to maximize the profit, right?
Right, right.
Yeah, but objective function looks like you maximize the spending.
The spending? No, because this is what you're making, right? That will be a positive number.
Yeah.
And the rest of this equation is gonna be a cost, right? So I think maybe you're getting confused because these parameters or these coefficients are bigger than this, right?
So the first time it shows the weekly profit.
Weekly profit, yes.
We need to the first brackets are profit, right?
This is profit.
And second two brackets will be like the cost that you deduct from profit.
This is the cost associated of producing the items. So if you sell it by 12, if you sell it for $12, but it costs you $6 to produce, then your profit is $6 for the first one. If it costs you $8
It's already, okay.
and
It's
you,
already deducted.
yes, so you spend $4, it's $4 profit, 15, you spend 8, is $7 profit, and then you have to subtract this cost of renting. But this is a one-time cost, okay? So these are binary variables. One-time cost, and then this will give you a profit depending on how many units you are going to produce. But if we just formulate the problem like this, you can see that the solution is telling you you should produce 30 of product 1, you should produce 10 of product 3, 0 of product 2, but you see your decision variables are all 0. So this solution is incorrect because this is telling you you can produce these items without having to rent a machine. So how can you fix this formulation? And I think this is just a modeling trick. So now we're gonna add this decision constraints here that are connecting our X decision variables with the Y. And we have a very big number for each one of these constraints, and we are modeling this big number with M. Remember, Y1, Y2, and Y3, those are binary variables. So if we have, let's say, in this type of constraint, if we have 100, this is never going to be less than 1. So that's why we need to multiply this by a large coefficient that is going to be large enough to the maximum that you can produce for each one of these products. And the idea, again, is just to connect those two decision variables. This constraint is just a modeling trick that is letting you make, forcing Y to be greater than 0, in this case, 1, if you decide to produce anything. Like if you decide to produce X1, then this constraint is going to force Y1 to be 1. Because you are multiplying that, let's say, by 1,000. So if this is 0, this is going to be 0. The whole thing is going to be 0. So this has to be 0. But if this is 1,000 and this is 1, this is going to be 1,000. So you can produce any amount of X1 as long as it is less than or equal to 1,000. So again, this is a modeling trick, but it will serve the purpose of getting you the right solution. Because now, with that constraint, you're forcing the decision variables that are binary to be 1 if you decide to produce for any of these products. And you can see now that the solution changes. With that additional constraint, this is telling you best thing you can do is to manufacture only product number 3 and you're going to be producing 25 of those. Yes.
I understand. I did not exceed the 1,000. They were saying, oh, the 1,000. I'm multiplying by 1,000, but I just want to see how to get that x1. Oh, it's x3, 25.
Yes.
Can you show me like?
Oh, so in this case, I'm just giving you the solution. I'm going to talk about the solution methods in a minute. But this is the optimal solution. I'm just illustrating the difference between the formulations. To obtain this solution, we're going to use the branch and bound method, and I'm going to explain that in a few minutes. Okay. So for now, I just want you to see how these problems are formulated and how missing some of these constraints can give you the wrong answer. You need to be aware of those modeling issues. This type of constraint is used frequently when you have to link decisions, which is the case that we have here. We have two types of decisions that we have to make, but one is depending on the other. So how do you manage those? These are the link constraints. So those linking constraints are going to allow you to link those decisions that depend on each other.
Hey, why did we have why?
Because we didn't have these constraints. Initially, since we were not linking x and y, because remember, we are only going to make y1 equal to 1 if we decide to produce x1, or if we decide to produce items of type 1, right? So if we are not producing type 1 items, then y1 is going to be 0. Yes. Because we don't have the linking constraints. It will be 0. This solution is correct given this formulation. Okay, the solution is correct given the formulation, but the solution in terms of practical application is not right. Because we are not linking decision variables x and y in this formulation. X is showing up in this two constraints. Y is not showing up in these two constraints. So y1 and y2 has a cost associated with the objective function, right? So you don't want to add cost to your decisions. So obviously this is going to be 0, because if you make this 1, it's going to decrease your profit, right? But now, since we are linking those decisions, we are telling the model, you know, if you choose to produce any of these products, you have to make these y's greater than 0 or 1. So that's why the solution is changing. Now we are forcing y1 to be different than 0 if we end up producing any of these products. So that cost will be there. And that's what we want. From the practical perspective, the solution should include that cost. So that's why you end up producing less items, because now you're only producing items of type 3, and you have a cost associated with that. So it kind of makes sense, right? Because the most profit and the less cost. Yeah, so you're going to force your solution to go that direction. Okay, so the fixed charge problem. Why is a problem with the characteristics of the previous problem called the fixed charge problem? In a fixed charge problem, there's a cost associated with performing an activity at a non-zero level does not depend on the level of the activity, which is the fixed charge of renting a machine. Practical applications like facility location problems. So if you decide to build, then there's a cost associated with that. If you don't build, there's no cost associated with that. And production planning problems like this one, in which you have a cost of a resource if you decide to go with one product, but if you don't do that product, there's that resource not used, so you don't have the cost associated with that. So that set covering problem. This is a third example we're going to go through before we talk about the solution methods. So in this problem, we have 6 cities. the county must determine where to build fire stations. Okay, so in this table, we have the time required to travel between cities. So 6 cities, and from 1 to 1, there's no time, right? So you're already in 1, so there's no time traveling there. But if you go from 1 to 2, it takes you 10 time units, let's say 10 minutes. From 1 to 3, if you have your station located in 1, it's gonna take you 20 minutes to get to 3. It's gonna take you 30 minutes to get to 4. It's gonna take you 30 minutes to get to 5, and it's gonna take you 20 minutes to get to 6. If you place your station in 2, city number 2, it's gonna take you 10 minutes to get to 1. It's gonna take you 25 minutes to get to 3, and so on. So depending on where you place these fire stations, you know that there's gonna be different times in terms of you getting to those other cities. So the city has 6 options and is trying to make a decision in terms of where to build these fire stations. We're gonna take into account these times to make those decisions. And the city wants to have the stations located so they can reach most of the cities within 15 minutes, or all the cities within 15 minutes. So we have taken this information and we have found, like, if you place it in 1, you can only reach 1 and 2 in 15 minutes. If you place it in 2, you can only reach 1, 2, and 6 within 15 minutes. If you place it in 3, you can only reach 2, 3, and 4 in less than 15 minutes, and so on. Yes, so it's less than 15 minutes. Yes, so you can get to that city in 10 minutes or 15 minutes or less. Good question. So the county wants to build the minimum number of fire stations needed to ensure that at least 1 fire station is within 15 minutes of each city. So the question is, how many fire stations should be built and where they should be located? So again, these problem have decision variables that are binary. So 1 if you build in the city, 0 if you don't build in that city. The objective function is to minimize the number of fire stations. So summation of all of them. So if we build in 1 in each city, we're gonna have 6 as the minimum. But we know that we are looking for less than 6 for sure. So what is the minimum? And here we have the constraints. So if we look at the table here, we have city 1 and 2, city 1, 2, 6. So those are going to help us write these constraints. So we are forcing the constraints x1 and x1 plus x2 has to be greater or equal to 1. So this is the constraint for city 1. X1 plus x2 plus x3, this is the constraint for city number 2. Right? And then we go to 3, is 3 and 4. X3 plus x4 has to be greater or equal to 1. And same thing here, we can reach 3, 4, and 5 from city 4. We can reach 4, 5, and 6 from city 6. City 5, and 2, 5, and 6 from city 6. So all these constraints greater or equal to 1, because we want to make sure that we at least get that we get to every city with the minimum number of fire stations. Okay, so for example, these first 2 constraints are the only ones having x1 and x2. So if we make x1 equal to 1, then we know this constraint is going to be satisfied, and this constraint is also going to be satisfied. So in that case, we don't need x2 and x6, because we know if we place it in 1, we're going to be able to cover 2 and 6. Right? So both, just by making x1 equal to 1, we're going to be able to satisfy these 2 constraints. In this case, if we make x4 equal to 1, we know that we can satisfy this group of constraints. Right, so what I'm saying is, go back here. So for example, if we make x1 equal to 1, then these two constraints are satisfied. If we make x4 equal to 1, these three constraints are going to be satisfied. And then we need, these two are not making the last one being satisfied. So if you look at that strategy, we can solve this problem visually. Can you get the optimal solution from this? Can you find the minimal number of fire stations by just looking at these constraints? X1 equal to 1 means that you're placing the fire station in city number 1. Yeah, X2 means that you're placing the fire station in city number 2, X6. But what this constraint is telling you is, if you place it in 1, the first constraint, if you place it in city 1, you can also reach city number 2. So there's no need for you to put a fire station in X1 and X2 because they're going to be overlapping. The service will be overlapping. So the question I have is, yes, and the answer is 2. So the minimum will be 2. So how do you get that solution?
Number 2 and number 4.
X2 equals 1 and X4 equals 1. Why is that? Because if you make X2 equal to 1, then you will satisfy this constraint, and this constraint. If you make X4 equals to 1, you're satisfying all these constraints with a minimum number of fire stations. Okay, and this is called the set covering problem. You have an area, you want to provide service to coverage to these areas. You're trying to identify where to place these facilities. This problem comes in multiple applications. For example, hospitals, clinics, healthcare in general. You want to make a decision in terms of where to place our next hospital or your next X-ray facility or cancer treatment center. You want to make sure that you cover certain areas. Also, if you think about telecommunications, like if you need to set up towers for wireless service. So how do you decide you want to provide service to these areas? That's another application. And so on. So you can find multiple applications for this set covering type of problem. So the optimal solution for this problem is X2 and X4 equal to 1, as you just saw. Set covering problem, we are given a set of objects. We are also given a set of subsets of these objects S. Each subset U has a cost associated with it. The problem to cover all the members of S at a minimum cost using the members of U. Properties, the problem is a minimization and all constraints are greater or equal to. All right-hand side coefficients are 1 and all other matrix coefficients are zeros or 1. Okay, so that's in terms of what integer programming is and different applications. So now we're going to transition to the solution methods. So as we learned for linear programming models, we have the simplex method. For integer programming models, we're going to have a different strategy to solve these problems or different algorithm. Integer variables makes an optimization problem difficult to solve. Memory and solution time may vary or may rise exponentially as you add more integer variables. Even with highly sophisticated algorithms and modern supercomputers, there are models of just a few hundred integer variables that have never been solved to optimality. This is because many combinations of specific integer values for the variable must be tested Each combination requires the solution of a linear or nonlinear optimization problem, and the number of combinations can rise exponentially with the size of the problem. So, so basically, when we say it rises exponentially, means this. So this is the curve of the exponential. So as the size increases, say size, and this is solution time. So as the size increases, the solution time also increases exponentially. So that's drastic. When we say exponentially, means that the change is very drastic. So the number of combinations can rise exponentially with the size of the problem. So solution methods, we're going to talk about the branch and bound. We'll yield the optimal solution, more efficient than total enumeration. Total enumeration basically looks at every possible combination and try to find the best. So this is very time consuming. So we're going to look at the branch and bound method and see how it works. So branch and bound method, usually IPs are solved by some version of the branch and bound procedure. Branch and bound methods implicitly enumerate all possible solutions to an AP or integer program. And by solving a single solved problem, many possible solutions may be eliminated from consideration. So the idea is you find a solution, you branch, meaning that you explore that solution space. And if you find that one branch gives you a better solution than the other one, then you can prune that branch and you save all that time of not exploring that time. And you just keep exploring on the branch that is giving you the best solution. So that gives you an advantage in terms of computational time, because you don't have to search for every possible combination. As you move forward in the algorithm, you're basically choosing which branch to explore and then eliminate some of the branches. So you know that those branches are not going to give you a better solution. So we're going to look at this problem, a manufacturing company for tables and chairs. Tables, you have some labor hours in terms of tables and chairs, square board feet of wood that is needed per product, and the profit. Currently, 6 hours of labor and 45 square board feet are available, and we want to formulate and solve an IP to maximize the profit of this company. So in this problem, again, we're going to look at the problem from a small size problem to decision variables. We have the number of tables manufactured, number of chairs to be manufactured, our decision variables. We want to maximize the profit, and we have a couple of constraints for labor constraints and materials constraints. And we want our decision variables to be integer. So the branch and bound method, step number one is to solve the LP relaxation of the integer programming. So we're going to solve the problem assuming that the constraints for the integer solution are not there. We're going to relax that constraint and we're going to find a solution, an initial solution for the problem. Solving the problem as a linear programming model. So for this problem, this is the feasible region. That blue area right here. And if we solve the problem using the graphical method for the linear programming case, we can find an optimal solution. That is this point. And as you can see, that optimal solution is fractional. Okay, so that's the LP relaxation solution. Okay, so we have a solution that is fractional. Z equals 165 over 4, x1 equals 15 over 4, x2 equals 9 over 4. Okay, so we got an initial solution, but we know that this solution is not integer. So we have to apply the branch and bound method now to explore this solution space. As a rule, the optimal value of the integer programming model is always less than or equal to the optimal value of the LP relaxation, which means that the solution that you obtain for the linear programming solution is always greater or equal to the integer solution the integer programming solution. And you saw why, right? The integer solution feasible region is always inside the LP relaxation feasible region. So that means that the solution that you're going to obtain is always less than or equal to the optimal value of the LP relaxation. So what this means in practical words is that you're not going to be able to get a better solution than this one when you solve the integer programming model. Okay, so the optimal solution of the integer programming will not give you a profit higher than this. That's the practical meaning of what I just said. So you know that you're going to have that upper bound in terms of how far you can go in terms of your optimal solution. This implies that the optimal value for the IP cannot exceed this Z value. The optimal value for the LP relaxation is an upper bound for the company's profit. Step number 2, we're going to partition the feasible region for the LP relaxation in an attempt to find out more about the location of the IP's optimal solution. So we're going to choose arbitrarily a variable that is fractional in the optimal solution to the LP relaxation. So you can choose either one. In this case, both of them are fractional. So we're going to choose one of them arbitrarily because we are going to explore in using that decision variable. So in this case, we're going to choose H1. Observe that every point in the feasible region for the IP must have either x1 less than or equal to 3 or x1 greater or equal to 4. So what this means is that we're going to find the integer values that are closer to this fractional number, right? So those are 3 and 4. This fractional value is in between 3 and 4. So what we're going to do is, okay, we know that if this solution is going to be integer, it has to go up and down this range, right? It could be 3 or it could be 4. I don't know which one it is, but has to be in that area. Okay, so observe that every point in the feasible region for the IP must have either x1 less than or equal to 3 or x1 greater or equal to 4. With this in mind, we branch on the variable x1 and create the following subproblems. Subproblem 2 will take the original problem and will add a constraint for x1 greater or equal to 4. And subproblem 3 will add a constraint for which x1 is going to be less than or equal to 3. So this is what we call branching. We're going to take one of the decision variables and we're going to find the closest integer values to that decision variable, and we're going to add constraints associated with those values. So in this case, 3 and 4. Because 3 and 4, because 15 over 4 is between 3 and 4, I'm going to add those two constraints to my problem and see if I can obtain a solution that is integer. So that's what this is representing. Okay, so this constraint right here is x1 less than or equal to 3. And this constraint right here is x1 greater or equal to 4. So what I'm doing now, I'm splitting the feasible region in 2 areas by adding these additional constraints that are forcing x1 to cut the feasible region when x1 equals 3 and cut the area where x1 equals 4. And we are creating 2 new problems. Okay, we are creating a problem which is what we call this problem right here. Is subproblem 2. And this piece right here is subproblem 3. Because subproblems 2 and 3 were created by adding constraints involving x1, we say that subproblems 2 and 3 were created by branching on x1. Okay. So step 3 will be to choose any subproblem that has not yet been solved as an LP. Okay, so we're going to choose between these two, subproblem 2 and subproblem 3. Okay, so that's they're being named here again, subproblem 3, subproblem 2. The optimal solution to subproblem 2, if we continue solving this using the graphical method, remember this is your isoprofit line. Where is it? So this is the isoprofit line right here. So if you move that line parallel to it in this direction, the last point that is going to be touched for subproblem 2 is going to be that point. So that will be the optimal solution for subproblem 2. And that will give you a z value of 41 with x1 equals 4 and x2 equals 9/5. Okay, so 4 and this value will be 9/5, almost 2. And you can see now that the optimal solution for subproblem number 2 has one of the decision variables that is integer. Okay, so we are making progress, right? X1 equals 4, but we still have a decision variable that is fractional. So if we start putting together these solutions, as I mentioned already, we're going to start branching, right? So these are the branches that we have created so far. We have the original problem, which is here at the top. We have the fractional values associated with the LP relaxation. And then we branch using these two constraints, which are based on this decision variable. We're branching for x1. And we solve one of the subproblems. We solved this one. We haven't solved this one yet. The optimal solution to subproblem 2 did not yield all integer solutions. So we choose to use subproblem 2 to create two new subproblems. Okay, so now we're going to continue branching in this direction because we know we are making progress. Now we have a decision variable that is integer. What if we branch for x2 and we can obtain also an integer solution for x2? So that's what we're going to attempt now. Choose the variable that is fractional in the optimal solution to subproblem 2. That will be x2 equals 9/5 and branch. Partition the feasible region for subproblem 2 into those points having x2 greater or equal to 2 and x2 less than or equal to 1. So again, 9/5 is between 1 and 2. Right, so 9/5 is in between 1 and 2. So the branches that we are going to add for this decision variable are those associated with the integer values that are closer to 9/5. So in this case, that will be x2 greater or equal to 2 and x2 less than or equal to 1. And we're going to create the following subproblems. So now we're going to take subproblem 1 plus constraint x1 greater or equal to 4, and we're going to add x2 greater or equal to 2, which is going to be equal to subproblem number 2 plus constraint x2 greater or equal to 2. And we are going to also create a subproblem 5, subproblem 1 plus constraint x1 greater or equal to 4, and x2 less than or equal to 1, which is going to be equal to subproblem 2 plus constraint x2 less than or equal to 1. So if we just focus on this subproblem number 2, and we add this constraint, so the constraints that we are adding now are in terms of x2, right? So this is the first constraint. And this is the second constraint. So this will go in this direction, x2 greater or equal to 2. And this one will go in this direction. This is x2 less than or equal to 1. And you can see that this constraint at the top subproblem 4 would be the area above this constraint. And you can see that that area is not touching the feasible region, right? So that's not going to have an impact on our solution. And then subproblem 5, it is under. So that's actually having an impact on our feasible region. Which is this region here for subproblem 5. So we attempt now to solve these two subproblems. Again, we are going to use our isoprofit line, and we're going to move that in this direction to find the last point that is touched in this area by that function. So we see that subproblem 4 is infeasible, right? Because x2 is greater or equal to 2. So there's no feasible area there. So we can mark that as infeasible. That's what we are doing here, right? And it is because of this that I show you here. That constraint is not touching any feasible area. So the solution is not existent. But for subproblem 5, and since we get a subproblem that's infeasible, we don't have to search through that branch anymore. That node is phantom. So the set of unsolved subproblems consists now on subproblem 3 and subproblem 5. So we're going to choose subproblem 5, and we're going to attempt to find an optimal solution for this subproblem right here. And the optimal solution for this problem, as you move this isoprofit line in this direction, will be z equals 365 over 9. X1 still a fractional number, but now x2 is an integer solution. Okay, so this point gives you an integer solution for x2, but not for x1. So we are not done. The optimal solution to subproblem 5 did not yield all integer solutions, so we choose to use subproblem 5 to create two new subproblems. So the only value that is fractional in this solution is this 40 over 9. So we're going to branch again for x1. And the integer values that are here between 40 over 9 is 4 and 5. So we're going to add those two constraints to our subproblem. So we're going to create two new subproblems, 6 and 7, by adding constraint x1 greater or equal to 5 to subproblem 5, and x1 less than or equal to 4 to subproblem 5. So we are basically, remember, this is no longer an option. So we are branching in this direction now. We're adding x1 greater or equal to 5, x1 less than or equal to 4, and we are creating two new subproblems. And the set of unsolved subproblems are still this one, and this one. So by adding x1 less than or equal to 4, we are adding this constraint, x1 less than or equal to 4, and we are adding this constraint, x1 greater or equal to 5. We're splitting this subproblem into two new subproblems. And as you can see now, the feasible region for these new subproblems 6 and 7 are the following. So for subproblem 6, the feasible region will be just this point. For subproblem 7, the feasible region will be just this line. So for these new subproblems now, we have a feasible region that is just a line. And for subproblem 6, we have a feasible region that is just 1 point. So for subproblem 6, the problem is very easy to solve, right? Because we only have 1 point. So choose any subproblem that has not yet been solved as an LP. We choose first subproblem number 7. And if we move this line in this direction, if we move the isoprofit line in this direction, the last point that is going to be touched for subproblem 7 is going to be that point, and that's giving us an integer solution that says that x1 should be 4, x2 should be 1, and the z value is 37. So we have found a candidate solution for our problem, which is integer. But we are not done because we have two unsolved subproblems. So we need to find out if we can get a better solution from any of those two. So we have a candidate solution obtained in which all variables have integer values. This is going to be lower bound for the original integer programming model. The set of unsolved problems consists of subproblem 3 and 6. So now we are going to branch on those two. Choose any subproblem that has not yet been solved. We have subproblem 6. And again, that problem has just 1 point. So that will be the optimal solution for that subproblem. And again, we are able to find another integer solution. So that's also a candidate solution for our problem. But as you can see now, this solution gives you z equals 40 is better than this one. So we don't have to consider this one anymore. We have found a better solution. So far, our optimal solution is z equals 40 with x1 equals 5 and x2 equals 0. But we still have one subproblem to explore, subproblem number 3. Subproblem number 3 is this whole area. But the good thing about this problem is that even though that area is very big, we're going to be able to find an integer solution quickly. So choose any subproblem that has not yet been solved. And the optimal solution, again, by moving this isoprofit line, will be this point. And that point gives you a solution x1 equals 3, x2 equals 3, with z equals 39. Which is this branch, and that's also integer solution. And both this solution is 39, this one is 37, are not better than 40. We have finished our search. So the optimal solution for this problem is z equals 40 with x1 equals 5, x2 equals 0. So the optimal solution will be to manufacture 5 tables and zero shares with the profit of $40. And that concludes this lecture. I know this is not easy to grasp the first time you see it. Good thing about this lecture is I have recorded the video so you can look at the video on your own. We go back to this on Monday. I'm going to go with the branch and bound method with a different example. But my advice to you is to look at the video lecture on your own before Monday. And then be ready to ask questions. And we'll go back to this on Monday and also on the review on the week after Thanksgiving. So make sure that you pay attention. There's an assignment also associated with this. So make sure that you go over that. Is there any questions? Yes. It is complicated. Let's say that way. Yes. Yes. Challenging, complicated. Yes, but that's the way integer programming models are solved. And that's why from the beginning, I started saying solving these problems is very challenging. And there's a lot of research going on because of that problem. These are combinatorial problems. Again, you're searching for combinations. And as you increase the size of the problem, this becomes very, very big. You have to test multiple combinations. And that's why the branching, pruning strategy saves you time because you are discarding certain branches as you move forward in the process. And by discarding those branches, you are saving computational time because you are not exploring those branches. By hand is complicated. Obviously, these methods are being implemented in computer programs, but we need you to understand what's going on, right? So that's why we go through this painful process. Yes. Yes. Any questions? Good. So we'll meet again on Monday, and tomorrow I have office hours. So if you want to join, you're welcome to. Have a good weekend.